Welcome to EET1015C. This is Fundamentals of DC Circuits. My name is Professor Evans, and this is the first video in the course. For this video, we're going to discuss voltage, current, resistance, and Ohm's law. So here are the learning objectives for this video. We're going to start with a little bit of review of engineering notation. Then we're going to discuss the concepts of electric charge, voltage, current, and resistance. We're going to review how to determine the value of a resistor based on its color code. We're going to review how to measure voltage, current, or resistance in a circuit, and then we're going to talk about Ohm's law and how we use that to calculate an unknown voltage, current, or resistance. So first I'm going to start with a quick review of number notation and more specifically engineering notation. So in the engineering field, it is very common to encounter very large and very small values. Scientific notation is considered a power of 10 notation that provides an easy method to express these very large and very small numbers. In scientific notation, which you've probably seen before in another math class, and you definitely should have seen in the Intro to Engineering course, each number is expressed as a power of 10. The decimal value is between 1 and 10, but not actually equal to 10. So we have rules for expressing decimal numbers in scientific notation. You'll have to move the decimal point just to the right of your leftmost non-zero digit. And then you're going to determine the exponent by counting the number of places the decimal point was moved. And you're either going to move to the right or to the left. If the decimal point was moved to the left, the exponent is positive. And if the decimal point was moved to the right, the exponent is negative. So for example, the number 150,000 would be written as 1.5 times 10 to the fifth. Now, remember that if you don't actually see a decimal point in the number, it's assumed to be all the way at the end at the far right. So if my decimal point were right here, beyond this very last zero, I'd have to move that decimal point until it is right in between the 1 and the 5, so that I have a leading digit of 1. So in order to move that decimal point so that it's in between the 1 and the 5, I had to move it 5 spaces. Since I moved to the left, I have an exponent that is positive. So 150,000 would be written as 1.5 times 10 to the fifth. 3,750 would be written as 3.75 times 10 to the third. Again, we're going to take the decimal point, which is at the end of the number if you don't see it written anywhere, move it 1, 2, 3 spaces to the left, giving us 3.75, and multiplying that by a power of 10. In this case, our exponent is 3 because that's the number of spaces that we had to move the decimal point. Here's one where you have to move the decimal point to the right instead of the left, so that tells you that your exponent is going to be negative when you're done. We're going to take that decimal point and move it 1, 2, 3, 4 spaces so that it's just in between the 1 and the 6, and that gives us a value of 1.6 times 10 to the negative 4, since, again, we had to move the decimal point to the right. So that's a quick review of scientific notation. From scientific notation, we can now have engineering notation. It's a special form of scientific notation, where the exponent of 10 is a multiple of 3. That means that every time you move that decimal point, you're only going to move it in groups of 3. You're going to move it 3 times, or 6 times, or 9 times, or 12 times, but not anything in between. Once we do that, we come up with a method of writing our final answer in engineering notation, which comes with an engineering prefix. And these prefixes are noted in the table right here on the right. So for each group of 3 that we move the decimal point, we now get a prefix that is added to the unit of our number. So if I had to move the decimal point 3 times, I would have our number times 10 to the third, and that gives me a prefix of kilo or K. If I had to move it 6 times, that gives me a prefix of mega or capital M, etc. So as we go through this chart, you can see that the gray rows represent rows for engineering notation. So here's some examples of how we use engineering notation. Let's say that I take a measurement and I get 0.0015 amps. The A stands for amps. Well, engineers are going to use engineering notation with every number that they write. So instead of recording this number as 0.0015, which is also very cumbersome to say out loud, or to continue writing over and over and over, or to use in calculations, we're going to use engineering notations. We're going to move the decimal point, and we're going to make sure that we always move it in groups of 3. So start out by moving it 3 spaces to the right. 1, 2, 3. Now once you move it those 3 spaces, you're going to stop and ask yourself, should I continue going forward or can I stop here? In this case, we don't have any more zeros in this number, and stopping after the first 3 spaces is just fine. So we get the number 1.5 times 10 to the negative 3, and our unit is amps. Now, that 10 to the negative 3 is going to be replaced with an engineering prefix. Looking at your table, 10 to the negative 3 is going to be replaced with the prefix milli, which is represented with a lowercase m. So our number becomes 1.5 milliamps. Now, as an engineer, anytime I see the prefix milli, I automatically know that I don't actually have 1.5 of anything. I have 1.5 times 10 to the negative 3 of that particular number. So as an engineer, we're always going to write numbers in engineering notation, and we're always going to interpret numbers using engineering notation, knowing that we can't necessarily take a number at its face value. The notation tells us how big or small that number actually is. Another thing about engineering notation, engineers always have units. Every number has to have a unit. Without a unit, I don't know if this 1.5 represents dollars, seconds, feet, hours, a force, time, meters, meters squared. We don't know. So as an engineer, we never write a number without a unit. It is always going to have a unit, because otherwise that number has no meaning as an engineer. We have to know what that number represents. So as you go forward in this course and all of your engineering courses, remember that engineers use engineering notation for every number that they write, and every number must always, 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 100% of the time have a unit. So here's another example of engineering notation. Notice I have a very, very, very small number. Imagine having to speak about this number or type this number or calculate with this number over and over and over. It becomes extremely cumbersome. So we're going to move the decimal point 1, 2, 3. We still have a lot more zeros left, so we're going to move it 3 more times. 1, 2, 3. So now my decimal point is right here between that very last 0 and the 3. You could choose to stop there, and if you did, your number would be 0.35 times 10 to the negative 6 amps. That's perfectly fine. If you decide to move the decimal point 6 spaces and stop right there, that's acceptable. Or you could choose to go another 3 spaces, moving in a total of 9 spaces. And that would give you 350 times 10 to the negative 9. So it's up to you whether you stop after 6 spaces or 9 spaces. There's no definitive right answer. It all depends on your particular setup, the problems that you're solving, or the request of the person who's evaluating your work. But in this case, you could move the decimal point 6 spaces or 9 spaces. So if you move the decimal point 6 spaces, you have 0.35 times 10 to the negative 6, and that negative 6 gets replaced with the prefix micro, which is represented by the Greek letter mu. That's a U with like a little tail on the left-hand side. That's a mu. So 0.35 microamps. Or if you decide to move the decimal point 9 spaces, you end up with 350 times 10 to the negative 9. Replace the negative 9 with the prefix for nano, which is represented with N. Technically, it's the Greek letter eta, which is an N with a longer tail on the right-hand side, but using an N is acceptable for nano. Also, writing just a U for microamps is also acceptable instead of the mu. So this is how we might write this particular number in engineering notation. And for our last example, if we have 4,700 ohms, we're going to move that decimal point 3 spaces to the left, giving us 4.7 times 10 to the third ohms, and that 10 to the third is going to be replaced with the prefix of kilo, which is represented with a K. So This is some examples of how engineers write numbers using engineering notation. If you look on your notes, there are a few examples on there for you to try. My suggestion is that you pause the video right now, try these on your own, make sure that you can write each number in the correct engineering notation, and then come back for the answers. So here's the answer for number 1. You've got to move the decimal point 6 places to the left, giving you 47.85 times 10 to the 6th, or 47.85 mega ohms. For the second one, you could choose to move the decimal point 3 spaces to the right, which would give you 0.165 milliamps, or you could move it 6 spaces to the right, which would give you 165 microamps. These two numbers are equivalent, and you could pick either one and you would have written that number correctly using engineering notation. So either one of these is fine. For the third one, you'll notice that it's not really clear how to move the decimal point because you have an exponent that is 10 to the negative 2. It's not a multiple of 3, so it's not immediately clear how to move the decimal point. For this one, I suggest just writing this value. What is 1.5 times 10 to the negative 2? That would be 0.015 volts. Then you can move the decimal point 1, 2, 3 spaces to the right to give you a value of 15 millivolts. So now that we've reviewed engineering notation, keep in mind that for this course, every number that you write, you will be expected to write in engineering notation. For any homework assignment, for any lab report, for any pre-lab assignment, for any exam, your numbers must be written in engineering notation, and every number must have a unit. So you will see points taken off if you did not use engineering notation or if you did not include a unit in your answer. Again, this is very important in the practice of becoming an engineer. So now we're going to move on to some core concepts for the course. The primary goal of a DC circuits course is to help you understand the relationship between voltage, current, and resistance. And in order to do that, we first have to understand the idea of electric charge. Electric charge is a property of matter that exists because of an excess or deficiency of electrons. So if you think back to perhaps a high school chemistry course that you've taken, you studied electrons, protons, and neutrons, and you studied the idea of opposite charges attracting or like charges repelling. So if you have two positive charges, they repel each other. If you have two negative charges, they repel each other. But if you have one positive charge and one negative charge, they attract. Well, the reason why you have that attraction or that repellence is because there's an electric field that surrounds every charge. And it is this electric field that exerts the force on another charge, either to repel or attract. So when we talk about electric charge, we measure it in a unit of coulombs, which is represented with a capital C. And 1 coulomb, 1 unit of charge, 1 coulomb is the total charge possessed by 6.25 times 10 to the 18th electrons. So if you can think about that massive number of electrons, those are all negative charges, that total amount of electrons is what is represented by 1 unit of electric charge, which we call a coulomb. The reason why we have to understand electric charge is because the definition of voltage and current is derived from it. So voltage, which is represented with a V, is defined as energy, another word for energy is work, per unit of charge. So when we think about the idea of voltage, it's the amount of energy per unit of charge. And that can be expressed as a simple equation. Voltage is equal to work divided by charge. W is the energy or the work represented in joules, that's the unit for energy, and Q is represented in coulombs, that's the unit for charge. So whenever we discuss the idea of voltage, at its core, that's its definition: work per unit charge, or energy per unit of charge. 1 volt is a measure of the difference in potential energy between 2 points, where 1 joule of energy is used to move 1 coulomb of charge from one point to another. That's our official definition of what a volt is. A voltage source provides the electrical energy needed, or the electromotive force needed to establish current. So a voltage source is what is going to establish the flow of electrons in a circuit. Voltage can be supplied from batteries, fuel cells, solar cells, generators, electronic power supplies. These are just a few examples. As we go throughout the course and as you go throughout your textbook, you'll see circuit schematics or circuit drawings, and a voltage source may be represented by one of the two images you see here on the screen. This is a DC voltage source. So for this course, we're only going to focus on a DC voltage. A DC voltage is a direct current voltage. That just means that a constant voltage is continuously supplied to the circuit. Constant voltage. That's what this symbol represents. So this symbol may represent a battery or any other DC source that supplies the same amount of voltage as long as the circuit is connected to it. The symbol on the right is an AC voltage source. Now, you're not going to see this symbol until you take fundamentals of AC circuits in the future. So as you're going through the book and as you're going through your pre-labs and multisim, make sure you always have a DC source, not an AC source. We're not using this in this class. An AC source is an alternating current source, meaning that over time, the voltage that is supplied to the circuit will change in the manner of a sine wave. You'll learn more about AC sources and how an AC signal will affect a circuit when you take the fundamentals of AC class in the future. Next, we're going to discuss current. Current is the amount of charge, again, charge is represented by the capital letter Q, that flows past a point in a unit of time. So current is essentially a flow rate, a measure of the amount of charge that passes a specific point in a particular unit of time. I is what we use to represent current, a capital I. If you're wondering why we use I, think about the fact that a capital C is already taken. We use C to represent the amount of charge in coulombs. So I is the letter that we use to denote current. Current is measured in amperes, or we say amps for short. And the flow rate for current at its most basic form can be written as I equals Q divided by T, the amount of charge flowing past a certain amount of point divided by the amount of time that is passed. So again, we measure current in amperes. Current is a measure of a rate of flow. And 1 ampere is the amount of current that exists when a number of electrons having a total charge of 1 coulomb move through a given cross-sectional area, think about a wire, in 1 second. So that's what the definition of 1 ampere is, 1 unit for amps. When you are drawing circuits or when you are looking at images in the textbook or when you're building circuits in multisim, if you need a current source, this is what the symbol will look like. This symbol means that a constant amount of current is being supplied to the circuit. Once you set that level of current, that current will always be supplied as long as you have a load connected to the circuit. Our third concept is resistance, which is the opposition to current. Resistance is expressed in ohms, and it's symbolized by the Greek letter omega. In circuit schematics or circuit drawings, you'll see a resistor being represented by this symbol here on the screen. So now that we've talked about these three ideas, voltage, current, and resistance, let's sort of sum this up. And a great way to sum this up is to think about the water pipe analogy. This is a very common analogy to understand the difference between a voltage, a current, and a resistance. Now remember, voltage is electromotive force. It's a force that establishes the flow of current. If you think about a water pipe like the one on the screen, we know that water is going to flow down and out of the pipe going this way. But how do we know that's how water is going to flow? Well, there's a force acting on the water, and that force, in this case, is gravity. Gravity is the force that causes water to flow down and out the pipe. Well, the voltage in an electric circuit is that force that causes the flow of electrons, just like gravity is the force in the water pipe that causes the flow of water. Current is the flow rate of electrons. So when you think about current, you can also think about the water pipe, such that if you look at these two pictures here, with a wider pipe, we have more flow. we have more flow of water. With a smaller, more constricted pipe, we have less flow. Current is a measure of that flow. How many electrons are flowing past a point in a given unit of time. So that's how we can think about current, the water actually flowing through the pipe and how much is flowing past a certain point. And then we have resistance, which is the opposition to the flow rate of electrons. So if I were to take a water pipe and put a crimp in the pipe, I restrict the flow of water past a certain point. That's what a resistor does. It provides an opposition to restrict the flow rate of electrons at a certain point. So these are our three ideas: voltage, current, and resistance. And the primary point of this entire course is to help you study various types of circuits that have a DC source, and how can we analyze the voltage, current, and resistance in each different type of circuit that we can encounter. So that's the point of this course, to understand these relationships as we look at various types of circuits that have a DC source. So as we go through the course, we're going to primarily be building circuits using resistors. So in order to do that, we need to review the resistor color code and make sure that you can properly calculate the value of a resistor based on its color code. You should have seen this in your intro class, and we're just going to quickly review it now. So just remember that each resistor has a band of colors across the middle section. Those colors represent a code that explain how much resistance that particular resistor has. So in the example on the screen, you can see that there are some bands across the resistor. We have red, black, yellow, and then a silver band all the way to the right. So whenever you have a resistor with 4 bands, the first 2 bands represent the digits. So with each color that you see, that color is represented by a digit. So if you look at the color red, you're going to use this table over here to figure out what digit does the color red represent. The color red represents the digit 2. The second band is also a digit, and it represents your second digit in the number. So you're going to look at the color is black. So you're going to go to the table and say, well, black is a digit of 0. So the value of this resistor is going to be 20. And then the third band is a multiplier. It means you're going to take these 2 digits, which form a number, and multiply it by something. Well, the third band represents the multiplier. So look at the third band, and you see that the color is yellow. So if you look at the chart on the right, take that color yellow and go over to the multiplier column. So we see that's 10,000, or 10 to the 4th. So to calculate the value of this resistor, we're going to take 20, which makes the number 20. We're going to multiply by the value of the multiplier band, which in this case is 10,000. That gives us 200,000 ohms. 200,000 ohms. But remember, we're not going to write down 200,000 ohms. We're going to convert that into engineering notation, which means we're going to take the decimal point right at the end of this 200,000 and move it 3 spaces to the left, giving us a value of 200 kiloohms. Next, we're going to look at the final band all the way on the right. Notice there's a great deal of distance between the first 3 and this right band. That's your tolerance band. That explains the tolerance for this resistor, which basically means that in a perfect and ideal world, if you were to measure the resistance of this resistor, it would be 200 kiloohms. In reality, you might get plus or minus 10% of that. That's your tolerance. So I could have 10% more than 200K, or I could have 10% less than 200K. As long as I'm within that range, that resistor is deemed acceptable. If you were to measure a resistor and you found that its measurement was outside that range of tolerance, then you would probably throw that away and get a new one, because you can't really trust the accuracy of its resistance value. So this is how we decode a resistor using the color code. Some resistors might have 5 bands instead of 4. If you have a 5-band resistor, the first 3 bands are digits. The 4th band is the multiplier. The 5th band is the tolerance. So with 4 bands, you have 2 digits. With a 5 band, you have 3 digits. That's really the only thing that will be different. So now let's do some practicing. If you have a resistor with the following bands: blue, black, brown, silver, what is its resistance value, and what is the range of acceptable values for that resistor? So you're going to use that chart that I showed on the previous slide to decode this resistor. The colors are blue, black, brown, silver. So you know that blue and black represent your digits. So if I go back here, blue is my first digit and black is my second digit. So I have the number 60. And then my third color is brown. That's my multiplier. Brown gives me a multiplier of 10. So I have 60 times 10. And then silver is my tolerance. So I have plus or minus 10%. So I'm going to go ahead and do this calculation. 60 times 10 gives me 600, and that will be 600 ohms. And in this case, I don't need to convert that to engineering notation. It's not too big, it's not too small, it's just right. If that were 6,000 ohms, I would rewrite that as 6 kilo ohms. In this case, 600 ohms is my answer, and I know that I have plus or minus 10% as my tolerance. That means I could have 10% more than 600 or 10% less than 600. So 10% of 600 is 60. So if I had 10% more of 600, that means I'd have 660 ohms. If I had 10% less, I'd have 540 ohms. So if I pick up a resistor from a kit and it says on the color bands blue, black, brown, silver, and I go to measure the value of that resistor, I know that it's expected to be around 600 ohms. It can be as low as 540 or as high as 660, and that is its acceptable or its actual resistance range. That's what we would expect it to be measured at. Here's our second example. We have a resistor with the following bands: violet, blue, gray, orange, red. What's the resistance and what's the tolerance? Notice you have 5 colors here, so you have a 5-band resistor. So the first 3 colors are your digits. 4th color is the multiplier. 5th color is the tolerance. So my first 3 digits are violet, blue, gray. That gives me 768. My multiplier is orange. That gives me 10 to the 3rd. My color for tolerance is red. That gives me plus or minus 2%. 768 times 10 to the 3rd would give me 768,000 ohms, or 768 kilo ohms. And then we have our range of plus or minus 2%. So then you need to calculate 2% of 768 and figure out the range by going 2% above 768 and 2% below. There's my resistance range for that resistor. In the third example, we're going to go backwards. We're going to determine the color code for a resistor that is 16.8 mega ohms plus or minus 10%. So I'm going to start by looking at the value of the resistor at 16.8 mega ohms. I have a 1, a 6, and an 8. That's 3 digits. So I have to figure out the digits. A 1 would give me brown, 6 would give me blue, and 8 would give me gray. So I know that my colors, my first 3 colors, are brown, blue, and gray. Next, I need to figure out the multiplier that's going to give me 16.8 mega ohms. So I know that I need 16.8 mega ohms, which is 16. You see it's 16, 800, 000. If we write that out, that's our 16.8 million or mega ohms. So we have to ask ourselves, if my digits are 1, 6, 8, what do I have to multiply 168 by in order to end up with 16.8 million? That multiplier has to be 10 to the 5th. 168 times 10 to the 5th gives me 16.8 million. So that means my multiplier has to be 10 to the 5th. And if you go back to your chart, that gives you a color of green. And lastly, our tolerance has to be silver because of the 10%. So our final answer, the color code for this resistor is brown, blue, gray, green, silver. In our last example, we're going to determine the color code for a resistor that is 14 ohms plus or minus 20%. Notice I only have 2 digits, so I know this is a 4-band resistor. I'm going to figure out the digits for 1 and 4. Those would be brown and yellow. And now I need to figure out what the multiplier is. Well, I have 1 and 4, which makes 14, and I'm not really multiplying by anything because I need exactly 14 ohms. If it feels like you don't have a multiplier, your multiplier is actually 1, or 10 to the 0. So that'll give you a multiplier of black. 14 times 1 will give you 14 ohms. And then the plus or minus 20%, if you look at your color code chart, you'll see that a tolerance of 20% correlates to no band. There actually is not a fourth band visible on that resistor. You'll only see 3 colors, which tells you that the tolerance is very high for that resistor, 20%. So our final answer is brown, yellow, black, and none for the fourth band. So that's a quick recap on how to decode resistors. You'll see in your lab kit that you will have several resistors that you'll have to use each week for your experiments. And you will need to be able to read the color code in order to determine the value for each resistor. So make sure that you have reviewed that and that you're comfortable decoding resistors as we go forward in the course. Now we're going to talk about some basic properties of electric circuits. So our basic definition of a circuit is that it consists of a voltage source, a load. Now a load could be a resistor or a light bulb, those are examples, and a path for current between the source and the load. The most important part of this definition is the part about the path. Current must have a closed path to follow. So if you look at the screen, you can see we have a picture of a battery connected to a lamp. The lamp is our load. The battery is polarized. That means you have 2 terminals right here. And they're labeled positive and negative. Current will begin to flow from the positive terminal and go around through the lamp, back out of the lamp, and into the negative terminal. This is our real-world scenario. On the right is a schematic or a drawing of how we represent that scenario. So our voltage source is shown right here. This symbol tells me it's a DC voltage source, which means it's going to deliver the same amount of voltage the entire time the load is connected. Current will leave the voltage source through the positive terminal, travel around the wire, through the lamp, out of the lamp, and back to the negative terminal. So this is our schematic that represents our real-world scenario, and the path must be a closed path so that current can return to where it started from in the beginning. You may also see that there are switches in your circuit. So here's the same circuit, but now we have a switch. The switch can control the path of the current. When the switch is closed, we have a complete path where current can flow out of the battery, around the wire, through the switch, out of the switch, into the lamp, out of the lamp, and back to where it started. That's a closed path. And we see that the switch is on or in the closed position, and current can flow completely around the circuit. If the switch is in the off position, or if the switch is open, we now consider this an open circuit. There's no current flowing in the circuit because there's not a closed path. This is how we represent this, like in multisim or by a drawing. Here's our open switch, and if we literally follow the path of current from the voltage source to this wire, and then from here, the current has nowhere to go because there's an open switch. So one of the most important parts in understanding your circuits as you build them throughout this course is understanding the flow or the path of current. Understanding the path of current is going to help you understand what's going on in your circuit. Here's another example of just understanding how current will flow in a circuit. So notice that we have a switch. The switch could be in one of 2 positions. It could be down in position 2 or it could be up in position 1. And depending on which position the switch is in, that will control which lamp is going to turn on. So if we look at the switch being in position 1, let's trace the path of current. Current will leave the voltage source. It will follow switch 1 around to lamp 1 and back around. Notice that lamp 2 never turns on because there's an open circuit right here. Current cannot flow through lamp number 2 because it's not connected to the path of current. Once the switch flips from position 1 to position 2, now we can see that current will leave the voltage source, go around to switch 2, through lamp 2 and back around. Notice current never flows through lamp 1 because there's an open circuit right here. There is no path for current to take. Therefore, the current cannot flow through lamp 1. Now, as we go through the course, we're going to talk about this idea of ground. Ground is a reference point in all electric circuits. It's the point from which all voltages are measured, and it's a common return path for an electric current. You have to have ground because it's your return path. The current will exit your particular voltage source, and it has to return to that same point in order for a closed path to be completed. Ground is that point of return. So you're going to see circuits in your book, in multisim, in these lectures. You're going to see each circuit have a ground. That ground represents our common return path for our electric current, and it also represents the point from which we're going to measure voltages. And that'll come into play in a few weeks as we talk about voltage drops. Now, the term ground originated from early studies in electricity, when one conductor of a circuit was literally connected to an 8-foot long metal rod that was driven into the ground. So that's where the word ground originated from. But as we go forward in this class, you're going to see circuits with a ground symbol. This is the ground symbol right here. Even though you see 4 ground symbols on one circuit, they all represent the same one point of return for the current. So if current is flowing in this branch, or this branch, or this branch, this ground symbol represents the fact that this is the point where that path leads directly back into the negative terminal of the voltage source, thus returning the current to its original starting place. So ground is going to be a very important part in this course. You're going to need to make sure when you draw or label circuits, you always have a ground. You have to have that reference point and that common return path. Now, the other thing you'll notice about these circuits on the screen is that they have different types of switches. So if we look at the top, this is a rotary switch. It can rotate between one of many different positions. Notice that if the switch is in position 1, that means current will flow from the voltage source up through to position 1 and down through lamp 3. Once it hits ground, this is an indication that current returns back to the voltage source, going in the negative terminal, and then going back out the positive. So this is our path of current when the switch is in position 1. If the switch were in position 2, we can see that current would flow through lamp 2. So our path of current would be from the positive terminal, through the switch to position 2, through lamp 2, to ground. Ground is our representation of returning back to the starting point right here. That's our path of current. And then with position 3, you can see that the current would flow through lamp 1. So notice only one lamp can be lit at a time because the switch controls the path of the current. Now on the top right here, you'll see a dual pole single throw switch. These 2 dotted lines here indicate that these 2 move at the exact same time. They move in tandem. They don't move independent of one another. So when the top switch is closed, the bottom switch is also closed. They work together. So when both of these are open, we can see that neither lamp will be on because there's no path for current to take. When both of these close, both lamps will be on because both paths will be complete. And so in this case, current is going to flow from the positive terminal, and it'll split. Some will go this way, some will go this way, and some will flow through lamp 1, and some will flow through lamp 2. Those 2 amounts of current will recombine at ground and return back to the voltage source. And that's your closed path of current. On the bottom, we have what's called a single pole dual throw switch, where we have one of 2 options. The switch will either be in connected to point 1 or connected to point 2, and current will be controlled by the connection of this switch. So we can see that when the switch is in point 1, current will flow through lamp 1. When the switch is connected to point 2, current will flow through lamp 2. Notice that this picture and this picture represent the exact same circuit. They're not drawn the same, Notice that lamp 1 is on the left, lamp 1 is in the center here. They're not drawn the same, but they are the exact same circuit. Why are they the exact same circuit? Because the path of current is exactly the same. And it's going to become increasingly important to remember that it is not about how the circuit is drawn or how it looks on a piece of paper. It is about how the current flows through the circuit. So the only reason why I can say these two are identical is because the path of current is the same. When the switch is connected to position 2, the current flows through lamp 2. Same thing happens here. When the switch is connected to position 1, the current flows through lamp 1. The exact same thing happens here. That's what makes these two identical. They have the exact same path or the exact same flow of current based on the position of that switch. So again, it's going to be very important that you don't rely on what it looks like. Rely only on the path that current takes to determine the relationship between the things going on in your circuit. All right, next we're going to review measuring current and voltage. This should be a review from the intro class. If you have a simple series circuit like the one shown here on the bottom left, you just have two resistors connected in series. You might use an ammeter to measure current. You might use a multimeter to measure current. So this is the multimeter in multisim. This is the multimeter you're actually going to use for your lab work at home. This is an ammeter that you can also use in multisim. So we have a number of different tools. The most important thing is, how do I place the tool into the circuit? Remember that if you want to measure current, the ammeter has to be placed in series so that the current can flow through it, directly through it. We call this breaking the circuit. So you have to break the circuit and insert the ammeter into the circuit so that all of the current can flow directly through it. If you want to measure a voltage, your voltmeter or your multimeter must be placed in parallel. That means that you have to connect your voltmeter on either end of the thing you want the voltage for. So you're not going to break the circuit. You're not going to redirect the path or the flow of current so that it goes completely through the voltmeter. You're just going to connect it on either side of the item you want the voltage for. So remember, ammeters are placed in series, voltmeters are placed in parallel. And a multimeter is just a tool that can do both voltage or current or resistance. And you have to make sure you physically set your multimeter to the correct measurement before you use it. Make sure also when you measure resistance, disconnect the resistor from the circuit to avoid damage to the meter or an incorrect measurement. And measure the resistance by connecting your two terminals to either side of the resistor. And polarity is not important here. It doesn't matter whether you have the red or the black on top or bottom. You're going to get the same measurement. That's not the case for current and voltage. Polarity does matter. We'll talk more about that as the semester goes on. And lastly, we're going to review Ohm's law, which again you should have studied in your intro class. We're just going to review it, make sure that it's fresh on your mind because we're going to be using Ohm's law for the entire semester. So when analyzing a DC circuit, a simple and helpful tool is Ohm's law. It describes the relationship between voltage, current, and resistance. So Ohm's law simply states that voltage is equal to current times resistance, or V equals IR for short. And although we generally say Ohm's law as V equals IR, we can always rearrange that equation so that we can solve it for I or solve it for R. So we know that V equals IR. That means that I is V over R. That means that R is V over I. Remember, I represents current. If you have a hard time remembering Ohm's law or remembering how to rearrange it, this pyramid is very helpful. So if you draw the pyramid, you put the V at the top, the I and the R at the bottom, then simply cover up what you want to find. So cover up the V, and how to find it is what's left. So you have I times R, I next to R, IR. If you cover up the I, you have V over R. If you cover up the R, you have V over I. So if you have a hard time memorizing or rearranging equations, this diagram can help you to remember how to use Ohm's law depending on what you want to find. And now let's do some quick practice using Ohm's law. We're going to use Ohm's law to find the missing value in this circuit. Notice I have a DC source right here. It's labeled as having a value of 100 volts. Look at the polarity. The polarity tells you the direction that current will flow. That's important, so we know current flows this way. Direction matters. And we have a resistor of 22 kiloohms. What we want to know is how much current is flowing in that circuit. So we're going to take Ohm's law, rearrange it so that we have I equals V divided by R. And then we're going to fill in our values for V and values for R. Now you'll notice that I didn't write 100 divided by 22. That would be incorrect. If you go to your calculator and you type in 100 divided by 22, you're not going to get the right answer. Why not? Because you don't have 22 ohms, you have 22 kiloohms, which is the same thing as 22,000 ohms. So when you go to do these calculations in your calculator, you can't just look at the numbers. You have to look at the numbers and the units and look at the engineering notation and make sure that you can type that in correctly. So when you're doing this calculation, you're not doing 100 divided by 22. You're doing 100 divided by 22,000. Or you can do 100 divided by 22 times 10 to the third. Or you can use the EE button on your calculator and do 100 divided by 22, hit the EE button, and hit the number 3. You should have learned how to use this or to do these calculations in the intro class. If you're not sure about how to type these things into your calculator, shoot me an email. We'll discuss it. Anyway, when you type this in, you'll get 100 divided by 22,000, which will give you 4.55 milliamps. Now, your calculator is not going to tell you that it's 4.55 milliamps. Your calculator is going to give you 0.00455, and it's up to you to convert that to milliamps. Or if you want to, if your calculator has the ability to change modes, you can put it in engineering mode, and then it will give you engineering notation in your answers. But that depends on the type of calculator that you have. If you don't have that type of calculator or you're not sure how to do that, then it's up to you to look at every answer that comes out of your calculator and manually write it in engineering notation yourself. Whether or not your calculator can do that for you, you should always know how to convert something to and from engineering notation on your own. So here's the next example. We have a 5 milliamp current that goes this way, our resistor of 56 ohms, and we want to know the voltage across the resistor, which is also the voltage of the source. So we're going to do V equals I times R. Again, when you write out your equation, don't fill in the I with just the 5. When you write this out on your paper, when you solve any problem on paper, you should be writing the number and the unit always so that you don't forget that you don't have 5 amps, you have 5 milliamps, which is 5 times 10 to the negative 3, or 0.005 amps. If you don't make it a habit of always writing your units, you're always going to type in the wrong numbers into your calculator. You're going to forget that this isn't 5, it's 0.005. So always write a unit. Always remind yourself, oh, that's milli. Milli is times 10 to the negative 3. And then when you do this calculation, you've got to remember to enter it into your calculator that way. So when you do 5 milliamps times 56 ohms, you'll get 0.28 volts or 280 millivolts. And then our last example, we have a circuit here, and instead of having labels on our components, we have meters. This meter is measuring a voltage. I know that because it's connected in parallel to the voltage source. And I have 150 volts showing as the measurement. So I know the voltage source is 150 volts. And I have a current meter here. I know it's measuring current because it's broken the circuit. It's inserted into the circuit. It's not connected in parallel. So that's measuring the current through the circuit. And I want to know what's the value of the resistor. So I'm going to plug in my values for voltage and current. Remember to write a unit with everything. Remember when you type this in your calculator, you're not doing 150 divided by 4.55. you're doing 150 divided by 4.55 times 10 to the negative 3 power. And then that's going to give you 32,970 kiloohms. I'm sorry, 32,970 ohms. And you're going to convert that to kiloohms by moving the decimal point 3 places and then adding your engineering prefix. So that's just a quick recap of Ohm's law. It's really a quick recap of things that, for the most part, you should have seen in the intro class, such as measuring resistors, measuring current and voltage, using the color code for resistors. I hope that most of this has been a quick review for you. As we go through the course, we're going to be relying on all of the things you learned in the intro course, and we're going to be building on that foundation. So, as always, feel free to reach out to me, send me an email, send me a Canvas message if you need help understanding something, if you need help reviewing anything. I will be more than happy to set up a meeting with you so we can go over anything that you need. And that is the end of this video.